Hey everybody, welcome to Bill Sky, the Assembly Guy, and we're going to start our discussion today with functions. How do we actually create a function in assembler language, and how do we use it? We're also going to go over how to set these functions up externally so we can link those functions into any assembler language program that we write. So we're going to be just generating an object file. And now, let me just say, this is going to be your introduction to functions. It's not going to be the quote-unquote right way to write functions, but it's a way to get started. And then when we start talking about stack frames in a few videos from now, we're going to go ahead and show you the right way to do it. So we're going to do this on Windows, we're going to do this on Linux, and we're also going to do this on ARM RISC processors. And those will all three be separate videos, so the videos aren't just huge, okay? So anyway, so let's get started with simple functions in assembler language. All right, let's do some function coding in ARM assembler language. So I have my Linux up here and running, and let's go ahead and create an ARM project. Now I'm going to stick with 64-bit here. So let's go into this Linux ARM 64-bit template. Where is that? There it is right there. I'm going to extract it. I'm going to rename it. And let's go ahead and look at the code. Now, ARM functions are a lot like normal Linux functions. ARM assembler functions are a lot like normal Linux NASM functions, where all you do is you specify a function name with a colon, and at the end you specify a return. Now, ARM doesn't have a call verb like Windows assembler language and Linux assembler language has. It just doesn't have it. There is no such thing. So if there's no such thing, then how do you return? How do you actually call a function? Well, there's a number of different ways. One way is to simply branch to add to, in this case add to the add2 function. And then right below it, you create a label called return. You can call it anything you want. Let's call it RET add2. And then down here in add2, you would say branch. When it's done, you would say branch to RET add2. Now we need a colon here. So let's see if that builds. Yep, builds just fine. But let's say we need to call the function again. Let's say we need to call add2 down here. Let's say we've done a bunch of stuff in between those two calls. And so we need to create another label below that our add2 knows how to go to. Well, there's a problem with that. I cannot create return add2 there again, because if I do, I get a already defined error. So I can't do that. So let's call this return add2, I don't know, B. So that built. But the problem is that the add2 function always returns the return add2, ret add2. So when we call it here, it'll return to here. When we call it here, it will not return to here. It'll return back to here. So now we have an infinite loop. There's no way we can get out of that. So if you're going to be creating a function that always returns to the same place, in other words, it's only called once in an entire program, this actually will work. However, it's not recommended. Not at all. So instead of this method, we can use a thing called the branch link method. And instead of branch to some label, we simply say RET. So you could say that the call in assembler, Linux, and Windows has been replaced by the branch link. However, the branch link is much different, and let's actually see it working. So I'm going to branch link to add2. And let's save and build that, and I put the RET at the bottom of the add2 function. So I'm going to go ahead and make that, and it built great. But what does branch link actually do? let's create a no-op right below that. Save and build that. So what's actually happening? When I say branch link, the link, what it does is it goes to the next statement. It puts the address of that statement, I believe, in the X30 register. So it'll stick it in the X30 register on 64-bit. I believe on 32-bit it sticks it in the R30 maybe. I can verify that. But so it puts it in there, and then when you say return, return takes the address that's in X30, puts it in the program pointer, the program counter pointer, which jumps us back to this line after the branch link. So that's pretty good. The problem with that, though, is that what if I need to use X30 somewhere? What's even worse is what if I have another function down here and add 2 branches and links to add 3. So let's walk through this really quick. So my start function, branches and links to add 2, that puts the return address of this no-op into X30. Here's add 2. We branch link to add 3. So what happens? It puts the return address of this no-op into X30. So now the return that was originally in X30 is gone. So you will never get back to that location. And in fact, this add to return will probably take you someplace and you get a segmentation fault or something. Could be a real problem. So branch link works, but we kind of need to use the stack. And we're not going to talk about that in this video, but we're going to talk about it in our stack frame video, our advanced functions after this. So again, ARM assembler language is much different than Intel x86-64 assembler language. It has less statements, and one of the statements that was taken out or was not implemented was the call using the stack. So with that said, just to kind of let you know what that actually meant, is that in x86-64 Intel assembler, it uses the stack to contain the return address, where should I go after my function is done, and then eliminates the whole problem. ARM uses the X30 register. So to do this yourself, you have to back up the X30 register. And one way that you can do that in this scenario is I could actually subtract. So I could say subtract from the stack pointer 16, and then I could store X30 into the stack pointer, the dereferenced stack pointer. And then that will save X30. And actually we need that. We don't need that there. We need that here. So we need to back up our stack pointer. So I'm going to put here back up our return address before we call this function. Then after we call that function, we will say load into X30 the dereferenced SP, and then add SP16. Restore our X30 return register. So what we're doing here in our first function called add2, we're going to back up our X30, which will have our return address in it. Then we branch link to add3. Then when that returns, because X30 will return us to here, then we recover our X30 register from the add2 call, the call to add2, so when it returns to the correct location. And let's see if this actually works. I'm going to put a no op here. And let's save and build this. And let's debug it. And let's see if this works. Okay, so here's our branch. And our branch took us to add 2. So we're going to make some room in the stack, store x30 in the stack, and now we're going to branch link to add 3. All add 3 does is does a no op and then returns. So let's see if this works. Yep, it returned back to the no op in add 2. Now we're going to load the old x30, the old return address, into x30. We're going to get rid of that extra room in the stack, and now we return, and it worked perfect. So you can actually imitate the call function or the call statement in x86-64 by putting the return address of your function or of the call to your function into the stack. And actually, it's a good idea to always do that. In every function that you create, you always back it up just to make sure that if you call another function from within, you do another branch link from within your function, you will get back to where you're supposed to get back in your code. And this is a little bit of an overview of stack frames, but not quite. This is a way that you can move back and forth in your functions. And it allows for multiple functions, nested function calls, a lot of people call them. So this is how you'll do what I like to call inline functions in ARM. Now, we haven't really done anything yet. So let's go ahead and do something. Our add2 function, and you really should have some comments in every one of your functions where you have a description of the function, you have the inputs, you have the outputs, and you might have an example of how to use the function. And you should always document your functions because then you can make that documentation available to other programmers that might want to use your functions, or it's a reminder as to what you did, what that function is all about, and if it's appropriate for what you want to do. So let's say for inputs, let's say x1 and x2 will be used as arguments. The outputs, x0, will contain the result of this function, and then up here in description, add the 2 arguments and place the sum into x0. So that's really what this does. And instead of 2 arguments, you might want to say 2 integer arguments. And then as an example, you might want to say load register x1, load register x2, branch link add 2, and that's an example of the code. So what's nice about these examples is that you can actually take that code and actually just paste it up in your actual source code, and your code's done. Now let's say if add2 is actually doing it. Well, it is really doing nothing but a no op. And I always like to have no ops before I restore my x30 and after I created it or after I backed it up. So what I'm going to do is I'm going to, let's say, load register x0 with 0. I'm then going to add x0, x1, and x2. So that's the code. So we put 0 into x0, and then we add x1 and x2 and put the sum into x0. Okay, let's take a quick look and see if that actually worked. So x0. Oh, so actually, okay, so we've got, I kind of lost my place. Let's take a look at our code and see what we're doing. Make sure we're doing it right. So we're putting 10 into x1. Okay, it's really a bad, I always like to have a no-op right here because that service or that interrupt right there, that SVC, it always executes this line of code, so it messes me up. Also, I don't think we built it. All right, so let's try it again. All right, so now we're going to move the value into x1, so that now has a 10. We're now going to move 20 into x2, so x1 has a 10, x2 has a 20. We're going to branch link to add 2. There's add 2. So we're going to put 0. Oh, no. So we're going to actually save our x30, our return address. We're going to branch link to add 3. I don't know why I did that. I should have taken that out. Okay. So now we're going to put 0 into x0. We're going to add x1 and x2 and put it in x0. You can see 30 now. We're going to restore our x30 return address, and now we're back to where we started. So it actually worked. Again, a little bit confusing on that debugging because I didn't take away this right here. So we don't really need to branch to add 3. So let's take that out of there, and now it'll be a little bit more clear. Now, something interesting about this that I thought I would show you, and this happens on ARM assembly language, doesn't happen on x86-64. While you're debugging, you're going to see some strange things. So notice in this line of code right here, I'm moving the number, hexadecimal number 10, I'm putting that into x1. But when you look at the debugger, we see load R x1. We see this strange number right here, 400130. What in the world is that? Well, in 64-bit ARM assembler, when you use a literal, an immediate value like that, what the assembler is actually doing, it's finding a place in memory to put the number 10, the hexadecimal number 10 in memory, and that's the address, 400130. So literals are used differently or are created differently or processed differently in ARM assembler 64-bit than they are in 32-bit or than they are in x86-64 Intel assembler. So when you create a literal and immediate like 0x10, it actually finds a memory location for it, the assembler, and it stores it in there. So you're not actually storing 400130, you're storing the number found in that address. And it's the same for 20. 20 is stored in 400138. So that's stored, that's in that memory location. And that's how those numbers get in there. Yeah, ARM is a little bit different when it comes to immediate values. So that's what those strange numbers are. Now if you remember, that was 400130. Well, that was 10. I really don't have a 0 anywhere because I wanted to show how that 0 will be saved anyway, everywhere. It'll actually use the same 0 that it used for other immediate values for 0. Let's go ahead and quit. Okay, so that's simple inline functions. Now what if I want to make this an object library? In fact, let's say I'm creating functions. I've done all this work to create my functions. I've got descriptions, inputs, outputs. What if I want to actually share it with other programmers, or I don't want to have to include that code in all of my source code. I just want to link to those object files. Well, that's actually pretty simple. Now I'm in Genie right here. What I'm going to do is I'm just going to click New, and I'm going to take my functions and I'm going to cut them out of my main program and paste them in here. Now I also need a couple of other things. Well, I don't actually need them, but I do it for completeness. I take these sections and I put them up there. And I've got my data and my BSS sections, and I've got my code section, which is .text. Now, why do I need data and BSS? Because if I want to create variables, if I want to create variables that are available only to my functions in this function library file that I'm creating, I can do it here. It's like creating a global variable for all of my functions. So I'm actually able to do that here. And then nobody will see them. Okay, so we've got that. Let's go ahead and save that. And we're going to, now Genie doesn't take me back to exactly where we were, so we kind of have to navigate a little bit. And I'm going to call this one SumFunctions.asm. So then Genie begins to highlight the data or the source code a little bit better. Now if I go ahead and build this, I now have an error. It doesn't know what add2 is anymore because I took the code out. So what we need to do is we need to specify, first of all, that add2 is external. So I'm going to say .external add2. So the assembler will work, but the linker will not. You will still get this error. So we actually have to modify the makefile. So when we create an external function library, we have to modify the makefile and link the object file created by the assembler for that external library with our main. So let's go ahead and open up our makefile. All right, here we go. So I now have to create a new target here, or recipe, and I'm going to call this one SumFunctions.o. It is going to be dependent upon SumFunctions.asm. And instead of main, we're going to change all those to SumFunctions.asm. We need to have a new line here under the clean. And let's do another one for the SumFunctions.lst file. So we've got a new recipe to build SumFunctions.o. That is our library. We already have our main.o that builds the ASM file for main, but main needs to now rely upon main.o and SumFunctions.o. And we have to include SumFunctions.o in our linker statement. All right, let's go back to our main and let's try to build it. And that's kind of interesting. Oh, yeah, that's kind of interesting. I actually did this earlier where I tested putting in .external into the program, and it worked fine. But I'm not sure why that's not working now. So normally you have to put external into your, and also under some functions, in your functions you have to say .global add2. And maybe I did that wrong. Nope. So the global works. And what does the global do? The global says that everybody has access to add2. We might also want to say global add3. So everybody has access to both of those. However, this version of the ARM assembler doesn't like external. So let's get rid of that. And it seems to have built okay. Now let's look back at our folder and let's take a look at what we've got there. Well, we've got SumFunctions.o. We've got our SumFunctions.asm. But SumFunctions.o, that's the file that you want to make available to other people or maybe to yourself. I might actually go into, I'm going to right click on that and say copy. I'm going to go to ASM projects and you can say see my libs there. That's for my Intel libraries. I'm going to create a new folder called my armlibs, and I'm going to paste that in there. So now any project I create, as long as I point the make file to the directory my armlibs and some functions.o, I don't ever have to look at that code again. I can just use it. It's really nice. I can just use it. Okay, for some, it's bothering me. So the reason why .external wasn't working is because it's .extern. Sorry about that. So it's always a good idea to have that in there so you know that the add2 is external. It depends upon the assembler. Sometimes it requires it, sometimes it doesn't. I don't know why. I think maybe 32-bit it requires it, but for 64-bit it lets the linker handle it. And I believe I actually read that. But anyway, I like to do things like this just to make sure that everybody knows that the add2 is external to this program. Okay, so now we're not using this my arm libs directory. We're using the ARM 64-bit. So let's actually see if this works. So I'm going to say make debug 1, file, new tab, make debug 2, and let's see if this works. Branch link to add2. Boom, I'm in add2. Add2 saves x30. It puts the data into x0, which is 0. It then adds x1 and x2. It restores x30, and it returns, so it works great. So now we have an external project, or we have an external library that we can then include in our projects. So I'm actually going to do that. Let's do that. I'm going to copy, let's copy all of this code, and I'm going to create a new project, and I'm going to use my external library. So I go back into ASM projects. I'm going to create an ARM 32. Let's stick with 64. And I'm just going to name this one test because I'm going to delete it after I get it working. Whoops. Huh. Okay, just a second. I got a little bit of a hiccup here. For some reason, the file manager will not let me rename. I think I might have found a bug. So what I'm going to do is I'm going to rename it. And actually, let's not rename it. Let's just go ahead and leave it there. Leave it that name because I'm going to delete it anyway. So yeah, every once in a while I find little problems like that. So I'm going to go into there and I'm going to change. Now I have to change my make file, so that's the first thing I'm going to do. So the make file requires me to include the sum functions. So the first thing I need to do is I don't have to create a new assembler recipe in my make file because the object file is already there. All I have to do is specify, and let's remember the name. It was my armlibs. Okay, some functions.o. Now let's quickly talk about this. What does this mean? It means the two dots mean go up one directory structure. So I'm in here right now. I'm going to go up one directory structure, and then I'm going to go into my armlibs, and that's where I can find some functions.o. I don't really need to change anything else here. Let's save that. Now I'm going to go back into my project folder. I'm going to edit my main.asm, and I'm just going to build it just to make sure things look good. Okay, So now I've got an external function called add2. I'm going to put some data in it. So I'm going to load into x1, 99, load into x2, forgot a 0, and then I'm not going to call. I'm going to branch link add2, and then put a no up there. Let's see if that builds, and it built. So that's how easy it is that you just have to modify your makefile to point, and I don't have to have that code in my current project. I don't have the object file. It's in the my arm libs folder. Now let's make sure this works. Oops. Huh. Oh, I capitalized it. There we go. Okay, let's see how this works. Okay, I load x1 and x2 with data. I jump to add2, and there's the saving of the x30 return address. There's the add. You can see now x0 has 1132. It returns, and my external function works. There's also the concept of an include file. Instead of you having to put all of these .externs for every function you want to use, there's also this idea of creating an include file. So I'm going to go into my arm libs, and I'm just going to open up a terminal here, and I'm going to say vim sumfunctions.inc and add my externs in there. I'm going to save that. And so now, instead of my project knowing what the external functions are, I'm simply going to say .include, double quote, // my arm libs / some functions .include. So that is how you would create an include file. I go from my current project up one level, go into the my arm libs, and go into some functions. The other benefit of this is that you can actually document your functions there. So instead of you should document them both in the assembly language code as well as the include file, but this way the programmer will not be able to see the documentation in an object file, but they will be able to see it in your include file. So this is a very good place to put it. So let's see if this builds okay, and it built just fine. All right, so one last thing I want to talk about here is how to back up your registers before you call a function and when you should do this. So I'm going to go back to my main here, and I'm going to take a look at my call to my function add2. And what I want to do is I'm loading data into x1 and x2. What if those registers have something in them that I need? Well, I have a couple of options. I can copy those to another register. So let's say I would load x5 from x1. Let's say I would put x1 into x5, put x2 into x6, call the function, and then I would restore them. I would then say load x2, x6, and I would say load x1, x5. So that's a way to do that, is that the ARM CPU has so many registers, it's actually pretty easy to do that. However, it is possible, you know something, let's build that to make sure it works. Okay, yeah, I don't think, so what did I do wrong here? Oh, does it move? Yeah. So when you're moving things between registers, just use move instead of LDR. Sorry about that. So anyway, but what if
you're using X5 and X6? What if you're using all of those registers? I know that there's so many registers that it could be kind of difficult to believe that, but it is possible. I have actually seen it happen. So instead of using registers to put the data, how about the stack? Now, if you watch the stack video that I did, I show you how to do this. But just to remind you, what you would do is you would subtract from the stack pointer 16. So we'd say comma 16. And then you would store x1 comma stack pointer. So this is the same as a push in x86 64. And then you would do the same thing for x2. And then when you're all done, you would restore them. And the way you restore them is you load x1 stack pointer. You would then add stack pointer 16. And then you would do, oh, not x1, you have to go backwards, right? You have to do it in the opposite direction that you pushed them. And then that restores your registers. Now it's really a good idea. Back up our x1 and x2 registers to the stack. So it's always a good idea to put comments just so you know what it is that you're trying to do. And then down here would be the restore. You know, I'm taking time doing these comments because they're so important in assembler. Okay, so let's go ahead and build that and make sure that builds correctly. Okay, good. So the next thing you have to think of is where do you do this saving of the registers? Do you do them in your functions? Do you do them in your main before you call the function? Well, one thing I like to think about is let's go ahead and take a look at the functions. So when you're making this decision, you've got to think about what is your function doing? Is it modifying your registers? In the case of add2, it really is not touching x1 and x2. So if that function is not modifying x1 and x2, it shouldn't be held responsible for backing them up. So in this case, our main would be responsible for backing them up because we're changing their values in the main assembler program. Now x0 is being changed, right? Because we're loading 0 into it and then we're adding the two numbers. But remember, and I may not have said this already, but x0 is normally like the accumulator register in Intel x86 64, where it's assumed that that will be the return value from the function. So any function that you call, it's assuming that x0, or if you're on 32-bit, r0, x0 will be modified. So if you need to save x0 before you call the function, it's always a good idea to stick it onto the stack. So you can just do this. The problem with that, though, is that if we restore it, we've just overwritten the return value that our add2 function performed. So we might want to store x0 at this point on line 33. We may want to store that to a variable or maybe put it in another register and then restore our x0. But x0, so you definitely have to think about this. What is it that you need to do to back up your registers? So yes, there's some design involved. And so you have to make that decision how you're going to do that with your registers, backing them up and then restoring them. So that are simple functions in ARM assembler language for 64-bit. 32-bit is a tiny bit different, but pretty easy to do. Sticking with 64-bit because it's the most modern technology. And what we're going to do next after this video is that we're going to look at advanced functions, where we start talking about stack frames and what all that means, Until then, see ya.